Thank you. I think it's probably 5 years ago when I got a call from David. David was the head of customer insights of T-Mobile USA. And he said, Frank, we got a problem. Too many customers are joining us. They all want to have a T-Mobile contract. So I asked him, what's the issue? Well, it's great. We don't know why. We don't know why they come. So actually what T-Mobile at that time were doing, they were eliminating contract terms, lowered the fees, they even gave free iPhones on top, and customers loved that. They had a great campaign and so forth. But they needed to know why they come, what of those components they did were driving them, because everything they did could be copied by the competition. So that's why we took a large set of market research data, brand tracking data, where they track outcomes and things, perceptions and things customers are doing. And what we found was basically the key for their future growth. We found that none of those items were directly causing people to buy. It was their marketing, their positioning to be the Un-carrier. We are changing wireless for the better. We are the Robin Hood of the industry. And those things that did, the contract terms, elimination and so forth, this was just a perfect reasoning why this storyline was true. And this insight basically was the reason why they then invented new kind of things like global roaming for free and so forth. That was a cornerstone to prove the storyline, and people continued to come. So I just wanted to show you this example that the quest for causality is universal. It is for when you want to make your football team better, want to drive better strategic decisions, if you want to be more successful in your life, or if you are in engineering. Everywhere, decisions are based on causal assumptions. I'll give you another example where we apply causal machine learning. So, second Bundesliga club approached us and said, we have tons of data. For every millisecond, we know where every player in the field is, how fast he is, what he does, and so forth. So we took this data and pre-processed that. We did time slices. For every action is basically a kind of a parameter profile, right? So, and we used then causal machine learning, which I will introduce you in a minute, to basically explain the future. Future outcomes are going, at least. We gained quite a lot of quite interesting insights. One of them is this one. Here we go. So there is a favorable shooting angle that is basically a trade-off between low defense and still having the possibility to hit the goal. So, and I give you just examples which show that there is something to it. Or do you know this one? So as you see, the quest for causality is worth it, right? So, and how do we today gain causal insights? How we drive decision making? So basically we look at correlations, right? And I give you here two patterns. This is a pattern of the mad cow disease outbreak. And now I show you the pattern of the Brexit votum, and suddenly there's a big correlation. So, this is how decision making is made today to the highest top levels of top businesses. So we can drive value to everyone, to every discipline in improving this decision making practice. So, and I would like to introduce you approach that I call universal structure modeling. And it's an approach which uses assumption for causality and machine learning. And we use and we build on 3 ideas which were introduced by Granger. And we advanced this idea of Granger. So basically Granger said 3 things. Something is a cause if it has information to predict the outcome. And only you need, of course, informations of all other possible other causes. So basically that's the confounder issue, that basically you need to assume that there are no confounders. Basically you have information about those confounders. And if this is the case, the closed world assumption is the case, plus the causes after the effect, then an information which is predictive is a cause. So we basically need to look at those three pillars. And what I would like to substitute the time lag assumption of Granger with other techniques, because often data is simply measured at the same time. But we still need to, basically this is what Granger is brought up and got his Nobel Prize for that. And basically what we found is leveraging machine learning is the best way to align to this idea that a cause is predictive. Let me explain to you how we do it. So basically we apply neural networks. What is a neural network? A neural network is a universal function approximator. And I can explain you now in 2-dimensional space how it works. So basically what you have is 2 input variables, 2 possible causes and an outcome, and you have here a hidden unit. A hidden unit is basically kind of a logistic formula. It is a nonlinear base function. This is a hidden unit. And with 1 hidden unit, you just have a kind of a wave. With 2 hidden units, you can superpose, basically the outcome node basically superpose everything, and you can form a kind of a wave. And if you superpose 4, you can shape more interesting landscapes. So what Kolmogorov 100 years ago has formulated is you can approximate any function with superposing nonlinear base functions. And this is what a neural net is doing. It superposes nonlinear base functions, and the learning mechanism tries to find the weights that brings basically a landscape which is best predicts the data. So the parameters has no meaning itself. That's why it's a semi-parametric approach. To give it in a so basically conventional statistics is parametric. You have a parameter, you assume linearity and independence of drivers. A neural networks basically has a flexible plane which adapts to data and can find any type of nonlinearities and any type of interactions in data. And actually it can find best, can I use an information to predict the outcome? It makes the best use out of the information at hand in order to understand is it causal or not. So, but it's not enough to fit the data. Therefore, you need to use certain machine learning approaches. If you use parametric approaches, you underfit the data, right? Because you imply assumptions that are not met by data, by the reality. If you use just machine learning, which tries to minimize the error, you overfit. You typically always overfit because you never have enough data. If you operate in large dimensional space, 10, 100 variables or so, there's a curse of dimensionality where you basically need always unlimited number of data. So that's why it's an imperative to do a regulated machine learning approach, which is a Bayesian neural network. There are others, but we use Bayesian neural networks because they have some useful properties. How does it do? This is the error function. It minimizes this error function. It consists of two parts. One part is the fit, the difference between the outcome and the prediction. Plus, there is the complexity term. It measures how complex is the model. Is it that complex or not? This is basically a weight of this. These are the weights of the neural network. If they are high, the model is complex. And what the Bayesian approach is doing is basically finding those hyperparameters. Now, the interesting approach is this hyperparameter exists for every input variable. So this means this learning mechanism automatically tries to minimize the complexity. It tries to prune out input variables. It reduces dimensionality space automatically. That's so much needed to not overfit and to gain useful information, which you can then say, okay, this variable is really carries information that is predictive for outcomes. So this is in a nutshell how we use machine learning, artificial neural networks to understand if something is predictive. So confounder, this is the second topic, and I just give you one example because confounders, I mention this because the Bayesian neural networks are very well designed to handle this as well. This is an example. This is a real data. Duration with the study of students correlate positive with income. So the longer you study, the more you will earn. That's a correlation. Obviously, this doesn't make sense because the smarter guys typically earn more, right? So there is a confounder. There is a variable which was not here. It's a type of study. People who, for instance, study chemistry, they do a PhD, they study longer, they earn more money afterwards. So, and once you put this information into the model will automatically find that the duration has a negative effect. So this means basically it's important to build large models, to build large causal models that include either the confounding or indicators that have information about the confounder. You may say, okay, I don't have the information which type of study in my data set, but maybe you have the information what kind of shirt people are using. Maybe they use proper shirts or t-shirts. So t-shirts are more used by chemistry students, and maybe there are placeholder indicator variables which also will be then useful to understand what the true impact of the duration is. And as I said, the Bayesian neural networks are designed to use many variables as well as variables with any kind of distribution, binary and whatever. And that's a big advantages over conventional statistical approaches. So, last point, causal direction. Of course, we need to build a good assumption about the causal direction beforehand. There are multiple of methods. One is Eckert has already shown that basically the idea of the C algorithm is, okay, when A and B does not correlate, it can't be the case that C influences A and B. This must be the case, otherwise they would correlate. So that's great. However, as he already told us, this it turns out that the algorithm for larger models tend to give a lot of errors. That's why you need to build on other or add other techniques to it to get a better understanding of the insights. One of those techniques is reading the noise distribution. Let me explain. So what you see here is, this is the same data, just x on y and y on x. And if you fit that with a regression, the error is the same. This is why you cannot use regression techniques to identify a causal direction. It's the same. But obviously you have an opinion about it, right? If you add an assumption that the noise is independent from the cause, then obviously the left part is the true causation. There are techniques that work better in a higher dimensional space, and others as well, so they need to be applied. And this is what we do in the universal structure modeling approach. It's an approach which involves the 3 steps. The first step is building the model. Basically, we connect every variable with every other, and we eliminate basically causal directions where we have some confidence that the direction is this way. Often you can even use prior knowledge to it. Nothing will change the gender. The gender will always influence of outcomes and so forth. So this is the first part, building the model. There are also for confounder testing methodologies, Hausman tests and so forth, which gives you some indications. Once you have set this model, we let the machine learning run. So every variable, every outcome which has influences, get its own machine learning neural network. So now we get a better understanding how things relate to each other. But one thing is missing. Machine learning neural nets are black box. They don't tell us how they came to their conclusion. They are pure prediction methods. That's why the third step is crucial. Simulation techniques to understand what the impact of those causal links is. Let me quickly illustrate that. So one way to illustrate and to visualize how A influences B is this. What you see here is basically the function of the neural network. Okay? It has an output. For every case, it has an output, a value. And if you take this function, but substitute one variable with a constant, for instance, its mean, you get the difference in those outputs. The difference is basically the impact of this variable. And yeah, this difference you can visualize on the y-axis, and this is this variable here. And you can see that, oh, there's a saturation effect. You can visualize the nonlinearities which the neural network already has found. And the same you do with interactions. So if you fix 2, if you combine those equations, you find 3D graphs which show you which interactions are at work. So suddenly neural networks are not a black box anymore. Another KPI we are computing is the average simulated effect. It's basically very simple. You take a variable and you increase their value, yeah, the effect. You just do a simulation for every single case in the data set. You increase it by 1%, and you look what's the prediction, how predictions are rising and falling. Yeah? It basically gives you the average simulated effect of changing the cause. We don't have parameters anymore. We have simulation results for concluding how effectful a cause is. So these are the different techniques used today. Most important ones: correlation, economic modeling, structure equation modeling, Bayesian nets, and universal structure modeling, which the difference is basically it's better able to control for confounders, and it identifies unknown nonlinearities and unknown interactions because of the machine learning approach, the neural networks. Yeah, so I'd like to conclude with a quote of George Box: "All models are wrong and some are useful." That's basically applies to causal models as well. You cannot prove causality. Still, it's imperative to build causal models because they improve decisions. They improve the likelihood that your decision will be successful. The proof is in the pudding, so to say. And let's look at the examples I showed you in the beginning. The Bundesliga team we consulted advanced in the first Bundesliga and even to the Champions League. And T-Mobile, they gained a lot of customers. They doubled customer, and now they bought Sprint and are even to the big competitors. Thank you so much. If you are interested, there are books at Amazon, or you can shoot me an email. I'm happy to send you also scientific publications about it. And I'm looking forward to the discussion.